Hey everyone, and today we're going to be doing a quick little series I found on internet. Let's get to it. It's going to be the sum from 1 to the negative 1 to the n over n squared plus n. So, like every series I've ever done, I'm just going to write down a few of these terms. When n is 1, we have negative 1 over 2 is 1 plus, and then for n equals 2, we have 1 over 2 squared is 4 plus 2 is 6. And then one more, this will be negative as well. We have negative 1 over 12. The main thing I wanted to notice when I did this was well, you didn't have to write the terms out, but the point is, for odd ends, we have negative terms. Even ends, we have positive terms. So what we're going to do is, knowing that, we're going to split the sum up into two separate sums. The sum of the odd terms, or the negative terms, and the sum of the evens, or the positives. Stuff with that. So first, we're going to write, this will be the odd ones. So the odds first, so this will go from n equals 1 to infinity, and we'll have just negative 1. Don't need the n, because the point is we're going to capture all the negative terms here. And then instead of n squared plus n, we're just going to replace that with 2n plus 1 for an odd number. 2n plus 1 squared plus 2n plus 1. Now, if we plug in 1 for this, we'll have the first odd number we end up getting is 3. So we actually don't get the negative 1/2 term. We start with the negative 1/12 term. Just going to add negative 1/2 out front. I could reindex the sum and have it go as n goes from 0 to infinity, but I don't want to do that. We'll just have this constant out front. Now, the main reason I want to do this is because now I can actually factor out the 2n plus 1 on the bottom. So let me do that real quick. We'll have negative 1 over 2n plus 1 times, and then this is 2n plus 1, this becomes 1, so we can combine terms. We have 2n plus 2. And from here, I can do partial fractions on this. So let me do that. Let me move this first. Now we have this just factored out sum. We're going to do partial fractions, so we're going to have a over 2n plus 1 be adding to b 2n plus 2. Of course, this will have to equal negative 1 over 2n plus 1 times 2n plus 2. From here, this is pretty standard partial fractions. I'm going to cross multiply, get a to n plus 2a. I'm going to have b 2n plus just 1b. And essentially what we're doing is we're trying to make it so these numerators will add up to get negative 1. It's to be negative 1 after we give them a common denominator. So now what we're going to do is, I notice there's a 2n term, there's two 2n terms, and we want it to equal negative 1. So no 2n term on the right-hand side. Which means that the numbers with the 2n attached to them as coefficients must go to 0. So we can just get rid of them. So we're going to have a plus b times 2n. I'm just factoring out the 2n. And we're going to add 2a plus b. This equals negative 1. We know that a plus b must equal 0. And 2a plus b has to equal negative 1. B negative 1. From here, this is a really basic system. I'm going to multiply the top by negative 1. This will cancel out the b's. We get a negative 1, which means b must equal 1. That's good. We got our partial fractions done for at least 1/2 of this sum. Write that down. We have -1 over 2n plus 1. And we're going to add 1 over 2n plus 2. This will be important for some afterwards, but for now, I'm going to move on to the evens. Let me write that down. Now the sum and goes from 1 to infinity of, since these are the even terms, they will always be positive 1 over 2n squared plus just 2n. And because plugging in 1 gets us the actual first even term, 1 times 2, 2 squared, 4. So this will get us our 1/6. Do not have to add a constant, so I'm just going to do partial fractions. So of course we'll factor out the 2n from the bottom. Have 1 over 2n times 2n plus 1. And then from here, basic partial fractions, we'll have a over 2n plus b 2n plus 1. This will equal 1 over n times 2n plus 1. Once again, we'll cross multiply. We'll have a 2n plus, I'm just going to cross multiply this, so we'll have the 2n terms collected. So we'll have b 2n, and we'll have the a times 1, which b plus a 1. Once again, we factor out the 2n's, and we realize that a plus b times 2n plus just a, that's equal 1. We know that a plus b to 0. And this basically tells us that a is 1, so this is that b must equal -1. Write this up here. We'll have 1 over 2n plus -1 over n plus 1. Now that we have our two series, let me just write them down in one place, and we're going to do a little bit of comparison with a well-known series to get what our actual sum is equal. We have, this is just going to be the odd one. I didn't have to write that out. I did not have to write this big line out either. So our odd series here, our odd series -1 over 2n plus 1 plus, we have -1 over 2n plus 1 plus 1 over n plus 2 down. And then this will be our evens or our positives. Let me just odd and terrible infinity. I cannot draw this infinity. Close enough. So this one will be 1 over 2n plus -1 over 2n plus 1. So what I wanted to do here is, once again, we're just going to write down a couple of the terms, and we're going to compare them to a very well-known series. For, and let me, before I forget, you in fact have to add the -1/2. It's not included. So, writing down our terms for the n equals 1 on the odd ones, we'll have -1 over 3 plus 1 over 4. It's for n equals 1, so parentheses, plus parentheses. We'll have -1 is for n equals 2. 5 plus 1 over 6. One more plus -1. 7 plus and this will obviously go on. The point is, this looks kind of like the alternating harmonic series. We have a gradually increasing denominator, decreasing size of the terms, sign flips, but let me write the alternating harmonic series here as just AHS. Slightly different. It's 1 minus 1/2 plus 1/3 minus 1/4 and on. But the point is, 1, we don't have, obviously, the -1. We have this -1/2 out here, but we'll do something with that after. And what we notice is it's -1/3 on our series, whereas it's 1/3 on the alternating harmonic series. This converges to ln2. So our series here, at least this portion of the series, should converge if it had the -1 plus the 1/2, should converge to something a little different. So if we had the negative alternating harmonic series, where you just multiply the above series by -1, this should be -1 plus 1/2 minus 1/3 plus 1/4, which looks a lot more like our series. This will converge to -ln2. So now what we have to consider is that for the odd ones, we don't actually have just looking at this, ignoring the -1/2, we don't have this 1/2 and we don't have the 1. So to account for that in what our sum converges to, we're just going to add the 1 and subtract the -1/2, or subtract the 1/2 from both sides. So our series is going to be -ln2, then we're going to add 1 minus 1/2, which should be plus 1/2, and then we have the -1/2 out here. We have -1/2. This will just equal -ln2. So we're going to say that our odd series here is going to converge to just -ln2. Now let's do the same thing with our even half. So we're going to have 1/2. Yep, 1/2 plus -1/3. This is for n equals 1, plus 1/4 plus -1/5. I don't think I have to continue for you to realize that this, once again, is also like the alternating harmonic series, or rather the negative alternating harmonic series, just without this plus 1, or this -1. So instead of converging to -ln2, we're going to add 1 to both sides, and this should converge to -ln2 plus 1. Now, since our original sum was made up of both of these, we have to actually add these. I'm going to add -ln2 plus 1 plus -ln2, and we're going to rearrange things. We're going to have 1 minus 2 times ln2. Instead of having 2 times ln2, using log properties, we're going to bring the 2 in. It'll be 2 squared. It's just ln4. ln4. This is what our sum converges to. So yeah, I used wolfram alpha to check, so I'm probably not wrong. But yeah, this is our sum. It's like -0.6 something. Yeah, thank you for watching.